Problem 1. A car comes to a bridge during a storm and finds the bridge washed out. Driver must get to the other side, so he decides to try leaping it with his car. The side the car is on is 30 meters above the river. Okay. Well, we have to make an assumption that it lifts off horizontally. That's the initial velocity. We know what's going to happen. I don't even have to read further yet. The opposite side is 2 meters above. The river is 50 meters wide. How fast? Okay, that's the initial velocity. Well, that's a projectile motion situation. A car is an object which is making projectile motion. So, what do we know? Well, the x component of velocity, which is equal to the velocity we are looking for, remains constant. And the range has to be equal to this velocity times the time we have to wait until it reaches the opposite side. And on the other hand, we can make an assumption that, well, the positive y-axis points up, so final vertical position should be equal to initial vertical position plus the initial velocity has no vertical component, 0 times time, plus, well, the acceleration points down, and we round it up. So that's the equation we have to solve for the time. So it turns out time is supposed to be equal to, well, that's 0. 30 minus 2, 28, 28, 56, 56 over 10, 5.6, square root of that's square root of 5.6 seconds. So the initial speed is equal to, oops, 50 divided by square root of 5 point, oops, clear, 50 divided by square root of 5.6 equals 21.1. Done. This is a problem similar to the one we did in a class. This is 10 meters. For the 45 degrees angle, the x component of velocity will be equal to the y component of the initial velocity. The equations are Vx equals V initial times cosine of 45 Vy initial equals this times the sine of 45. But cosine of 45 and the sine of 45 are the same, square root of 2 over 2. So that's got to be equal to the initial velocity, well, divided by square root of 2. The range, that's what we're looking for, and we know the range has to be equal to the initial x, which is, well, just Vx, it stays the same, times total time, which is, well, times 2 times time up, because time up and time down in this case are equal to each other. So now the maximum height is supposed to be equal to this equation has two unknowns, the vertical component of initial velocity and time up, so we cannot use this. Well, we have three equations, which we always can use. The second equation is the velocity equation. So at the highest point, the velocity has no vertical component. Still doesn't help. So what we really need is an equation which relates the height, because we know it, the acceleration due to gravity, because we know it, and, well, one of these variables, time up, or the initial component of vertical velocity. And, well, this equation doesn't work. So there's one more equation, number 3, which involves squares of velocities. So again, 0 squared, that's the final value of the vertical component of velocity. It's supposed to be equal to initial squared plus 2 times, well, acceleration is -10, and the vertical displacement from here to here is 10. So that equation has only one unknown. So that gives us about 14. I'm just going to keep 14. And as we know, this also should be equal to the x component. Now, if we know this number, which is 14, we can calculate the time up. That will be 14 over 10, 1.4 seconds. And now, because we know this, and we know this, it's 14, the range will be equal to 14 times 2 times 1.4, times 2 times 1.4, about 39 or 40 meters. All right, moving on. Well, what do we have here? This plus this plus this is equal to 0 because of this. How can it happen? Well, the given force should have the components which should cancel out the other two forces. So from this picture, the magnitude of the second force should be equal to the magnitude of the x component of the given force. Well, we choose natural directions, x and y, which has to be equal to 100, which is hypotenuse. Well, let's say times cosine of this angle. So if from here to here this angle equals 120 and this angle equals 90 degrees, x and y axes are perpendicular to each other, so 120 minus 90, this angle equals 30. 100 times cosine of 30, make sure degrees, about 86.6 newtons. Now from the same picture, so that's what we call Fx, that's what we call Fy. The magnitude of the first force should be equal to the magnitude of the y component of the given force, and that is 100 times the sine of 30, which is 50 newtons. So constant horizontal force is being applied to an object, smooth, which means no friction. So that's what we know. Object is speeding up. It travels 15 meters from rest, and it takes 5 seconds to travel to the final location. So, strictly speaking, in general, 4 forces would have been acting on it. That's the normal force, that's the force of gravity, that's the force of friction, and because we have to neglect friction, we can cross it out. Normal and gravity cancel each other out. They're not responsible for the acceleration. So F net, which is, well, normal plus gravity plus friction plus applied force, will be equal to just the applied force, which is 2 Newton, which is 100 newtons to the right. And that, according to the Newton's second law, should be equal to m times a. So if we knew the acceleration, that will give us the mass. How can we get the acceleration? Well, we can use the motion equation, we can use the velocity equation, or we can use the equation which relates speed squared and the rest of the stuff. So, the first equation, what does it relate? Well, it relates displacement, acceleration, initial velocity, and time. So, 15 meters should be equal to 0 plus 0 times time, well, 5, plus acceleration times time, which is 5 squared divided by 2. So the acceleration will be equal to, well, that's 30 over 25. .2. So the mass we're looking for should be equal to net force divided by acceleration. Oops. About 83.3 kilograms. Moving on. For this problem, we have two objects, and we can define three different systems. The easiest way is start from looking at this system as a whole. The total mass is 15 kilograms. Normal and gravity cancel each other, no friction, so net force is equal to 30, and it also has to be equal to 15 kilograms times acceleration, so acceleration equals 2. Now, if we treat this as a system, there are two forces, two horizontal forces acting on it, and this will be the contact force. If we look at this box, there's only one horizontal force acting on it here. So this is the force from B on A, this is the force from A on B, and according to the Newton's third law, they have the same magnitudes, opposite directions, but the same magnitudes. So we can calculate this, we can calculate that, doesn't matter. Calculating this is easier. So the mass of this is 5, the acceleration of this guy is the same, 2, 5 times 2 is 10. What we have here is the lab setup. So gravity and tension, gravity and tension. We can calculate this gravity equals, well, if you use International System of Units, 0.9 kilograms times 10, 9 newtons. 1.2 kilograms times 10, 12 newtons. So some people try to calculate the net force. Well, could work. Internal forces don't do anything. So the external force would be 12 minus 9, which is 3 newtons. But the net force is supposed to be divided by the total mass of the system. So it should be, well, 1.2 kilograms plus 0.9 kilograms to 0.1. But the straightforward approach is writing two equations. First, the Newton's second law for the little guy. Well, we choose positive y direction upwards, so everything which points up is positive. MA is positive, tension is positive, gravity has negative component, negative. Now here, initially we could have written negative MA should be equal to positive 10 plus negative mg, but by multiplying everything by negative 1, we make change from minus to plus, from plus to minus, from minus to plus, and then we're adding two equations, term by term. A is a common factor, little m plus big M, t and minus t cancel, and big M minus little m is here, times g. So if we're calculating the acceleration, this over that, the difference divided by the sum times g, and that gives us 1.4.